Hi everybody! Today I'd like to talk to you about inverse of exponential functions. And hopefully you watched the videos previously about inverse of a linear function and also inverse of a quadratic. So today we're going to talk about inverse of exponential functions. And hopefully you're also aware of an exponential function. So we're going to start with a nice simple exponential function having to do with doubling, and that is y equals 2 to the x. So if something's doubling over time, maybe you have 4 of it, then you have 8 of it, then you have 16, etc. So this growth becomes pretty fast over time. So we're going to start off with a couple of x values, simple ones, and notice the x values live in the exponent, and so that's what's causing this doubling. So you might start off with 1/8, and then eventually you have a fourth. And you can see that as this increases, you go from 2 to 4 and then all the way to 8. And so you have this pretty fast rise over time. And that's what we call an exponential function. You have what we call exponential growth. And so if you take a look at the domain, all real numbers for x, but the y values are all positive. In fact, that graph never crosses the x-axis, so y is never 0 and y is never negative. So let's talk about its inverse function. So we did this last time, and that is when we took the inverse on the graph, we switched all of the x and y. So if you look at all of those points, we're going to take those points and we're going to regraph them switched. So if you think about where 1/8 negative 3 is, or 1/4 negative 2, right? So we're going to graph all of those switched. And you can see this growth essentially does what we call slow down. So it goes real fast at first, but then eventually you have to go all the way out to 2 to rise to a height of 1, and then you have to go all the way out to 4 to rise to a height of 2, and 8 to rise to a height of 3. So that is the inverse of an exponential function. That's what that's going to look like. And again, we'll also switch the domain and range, because that's a thing that we do as well when we take the inverse of a function. We switch all the x and y points, and we switch the x and y's in the domain and ranges. You can see where it says x is all reals, now it says y is all reals, etc. So the next thing we're going to do is we're going to switch the x and y in the equation, because we want to rewrite this equation so that we can find the inverse equation. And so we'll take a look at y equals 2 to the x, and we'll switch all the x's and y's. And now we have x equals 2 to the y. And that's the equation of the inverse. That's that purple graph that you're looking at. However, we like to solve for y so that we can graph this in function. We can write the equation in function notation. And so we have a little situation, and that is that y is stuck up in the exponent, and we could try to take the y-th root, but we don't really know what that is. So we need a different tool to bring that y down in front. And I know exactly what tool we're going to use. We're going to use what is called the log. So a log is a really fancy tool, actually not so fancy, but it's a really handy tool that takes anything in the exponent and it can bring it down in front. And we're specifically going to take the log base 2. And so every log has a base, and there's a reason why we take the log base 2, and I'll talk about the reason in just one second. But by taking the log of both sides, log base 2, I'm going to drop that y down in front. I'm going to get y times log base 2 of 2, and on the left side I'm going to get log base 2 of x. Now what's nice is because I used log base 2 and 2, those cancel each other out, and they cancel each other out because they're inverse functions. How do I know they're inverse functions? Because I just flipped it on y equals x. So because that cancels out, I get y equals log base 2 of x. Really nice. So that's what that function's called, that purple graph. That inverse of 2 to the x is actually log base 2 of x. And so now we have a name for it. So f of x is 2 to the x, and f inverse of x is log base 2 to the x. They will cancel each other out. All right, so those two graphs. It's really nice because in algebra, a lot of times we need to cancel out exponential functions, or we need to cancel out log functions, and now we know which ones undo each other. Let me give you an example. If I had 2 to something, and in that exponent I had log base 2 of x, then those guys would cancel and I would just get out x. Or if I had log base 2 of 2 to the x, then those guys would just cancel and I would get out x. Again, inverse functions undo each other, so that's really, really nice. In fact, this is true of really any exponential function. So for example, if I had the exponential function of 3 to the x, so something that's tripling over time, then its inverse function would be log base 3 of x, right there. Or if I had 5 to the x, then its inverse function would be log base 5 of x. So notice every log has a base, and that base tells you essentially what inverse function it came from originally. That was an exponential function. So if I see I have y equals 5 to the x, that 0.15 now becomes the 0.51 on my log function. So that's why every log has to have a base number to it so that you can know where it came from, essentially. Really, really handy. So let's talk in general. Exponential functions are a family of functions. I got a whole ton of exponential functions. And logarithmic functions are also a family of functions. And you can see how they're related by looking at the base of every log. So if you look at y equals b to the x, then you're always going to get a log base b of x being its inverse function. So that's really nice. In fact, if you thought of the function e to the x, if you're familiar with the function e to the x, a log base e of x exists, and we never call it that. We just call it the natural log of x. So if somebody says, oh, I took the natural log, you know that they took the log base e of x. So it has the same meaning. Anyway, we'll do more on logs in the future. Logs are super handy in real life, and so are exponential functions for science and data and stuff. So I'll give you some more content on this soon, but otherwise, take care.